All right, so in the last video, we talked about what are the r and the theta mean. That was our first polar form of complex numbers video. Here, I'm going to take you through how you can take a complex number that's in rectangular coordinates, in Cartesian coordinates, and change it into polar coordinates, and then represent it in terms of sine and cosine. So let's take a complex number. Let's say we have the complex number -2 plus 2i. I can represent that as this point right here, which is -2 comma 2. I can connect that to the origin, draw a right triangle, 2 and 2. We can calculate our r. R squared is going to be 4 plus 4. So r is going to be the square root of 8. And then our theta, we can say tangent of theta. I guess this would be -2. Tangent of theta is 2 over -2 is -1. So theta is the inverse tangent of -1. But we also want to fix our quadrant there. And so making sure that we are getting the right value for theta, that it would be 3 pi over 4. So we had to add pi to what the original one was. So anyway, our theta is 3 pi over 4, as you can see if you just looked at like a unit circle. So what we can do is we can represent this as in terms of cosine and in terms of sine. Because if you think about a right triangle, we know that we can do the cosine of 3 pi over 4 is equal to um, negative square root of 2 over 2. And the sine of 3 pi over 4 is equal to positive square root of 2 over 2. And if you take those values and multiply them both by r, you're going to get back to our original rectangular coordinates for the complex number. So what do I mean? If you look at r equals the square root of 8, the square root of 8 is really the same thing as 2 times the square root of 2. So if I take 2 times the square root of 2 and multiply it by the cosine and multiply the r by the sine, I get back to my original one. So let me just show you that process. If I take r times cosine of theta, what does that become in this example? 2 times the square root of 2 times negative root 2 over 2. The 2's can cancel out and the square roots can cancel out, and it becomes the real part. And if I did r times sine of theta, I would have 2 square root 2 times positive square root of 2 over 2. And same thing, we cancel out the 2 over 2, and our 2 square roots become the imaginary part of it. And so the point is that you can take a complex number that's written in rectangular coordinates, in Cartesian coordinates, and you can represent it as r times the cosine of theta plus r times the sine of theta. And you should notice that both of those terms have the r value in common. And so the more common way that people will write this is they'll factor out the r, and then you'll have cosine of theta. Missed one piece. The imaginary part isn't just the number 2. The imaginary part has the letter I on it. So you'll put your I right here in front of the sign. You can put it somewhere on that sign value because that's the imaginary part. So getting back to what I was saying is both of those terms, even though there's the I and the sign value, both those terms have 2 root 2 in common. So you factor that out in front. So you have 2 root 2 times cosine of theta, 3 pi over 4, plus I sine of 3 pi over 4. Okay. In general, what you can do is take any complex number. Any complex number is written as a plus bi And you can represent that as r factored out of cosine theta plus I sine theta. In the next video, I'm going to take this idea and push it one step further. And this is going to be the next video will be the one where you need to use your knowledge of Maclaurin series in addition to these videos. And we're going to have that all tie together, talk about r e to the I theta. Okay, so thank you. Please ask if you need more videos about how do you go through the mechanics of changing a number from Cartesian to polar form or vice versa. Happy to make those. This was just a quick example to lead to the idea here that we can write a rectangular coordinate one in terms of polar coordinates and talk about it in terms of r and cosine theta plus I sine theta. All right, thank you for watching.